complex pedantic theorem.
I'm Tessa Monroe, and welcome to the pumped-up world of pre-algebra.
In part one of this two-part series, we're going to jump headfirst into the mathematical waters, exploring things like exponents, factoring, absolute value, square roots, inequalities, and oh, so much more.
Now, we know that pre-algebra can be kind of a rough ride at times. The standard deviants have scoured the nation for all the introductory pre-algebra material you need to know, and then hired some pretty awesome pre-algebra professors to help us. You can count on us to simplify the stuff and make it easy to learn, easy to remember, and just a little bit enjoyable. Believe it, it's our job.
Okay, you're watching a videotape that you either bought, found, or got as a present from someone who cares about you a lot. Because you're now watching this video, you have the power to rewind or fast forward at any time for any reason. And you can pause the tape if you want to write something down, look at it really closely, or if you need to take a break to practice for the International Hula Hooping Competition.
Now take your eyes and insert them into that box you got there. You should find a card with lots of really cool pre-algebra info on it. It's full of good stuff that'll be a handy review after you're done with the tape.
But remember, these videos are no substitute for class. They are of high standard, they are high quality, they are educational, but they are not the same as class. So go to class. You've gone once, you've gone twice, keep going to class.
Now that we got through all that intro stuff, it's time to get to the math. Sit back, relax, and grab a snack. Here we go.
So what do we mean by pre-algebra anyway? Well, it's not basic math, and it's not algebra. And it's not Imperial French history, the guillotine, and you. The best way to put it is to say that pre-algebra is all the stuff that falls in between basic math and algebra.
So, if you're looking for more basic stuff like adding, subtracting, multiplication, division, decimals, percents, and fractions, then you should pick up the zany world of basic math before getting into this tape. On the other hand, if you're looking to work with more complex equations, functions, and polynomials, then you probably want the adventurous world of college algebra. But if you're looking for the happy medium between the two, then you've come to the right place. So let's get moving with some things called integer exponents.
Part 1. Integer exponents.
Section A. What is an integer exponent?
What do we mean by integer exponent? Well, we're really just talking about certain kinds of numbers and the way those numbers are written. First, let's review what an integer is, then we'll get to exponents.
Remember from basic math that an integer is any positive or negative whole number and 0. So 8, 94, 6, -4, -23, and 0 are all integers.
An exponent is the small number you might see at the upper right corner of an integer. For example, if we see a 2 with a little 5 in its upper right-hand corner and a 3 with a little 4 in its upper right-hand corner, the 5 and 4 are the exponents. The 2 and 3 are called the base numbers. We read these examples as 2 to the 5th power and 3 to the 4th power.
So what does all this mean? It means that when we have a base number and an exponent, the exponent tells us how many times to multiply the base number.
Using our same examples, 2 to the 5th power and 3 to the 4th power, we write them out to look like this. 2 times 2 times 2 times 2 times 2, and 3 times 3 times 3 times 3. When we multiply our first set out, we get 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. That's 5 2's, which equals 32. Now for the next one. 3 times 3 is 9, times 3 is 27, times 3 is 81. That's 4 3's, which equals 81. So, when we have an exponent, we multiply the base number the number of times indicated by that exponent.
So, there's a base number, which we'll call a, and an exponent, which we'll call n, where n is a positive integer. When we talk about a to the nth power as a unit, it's called the exponential term.
As we get into mathematical operations with higher numbers, such as 5 to the 10th power and 20 to the 15th power, writing this out, or even punching it into a calculator, can be a pretty tedious task. In short, it's a big pain in the neck.
So within the exponential universe, exponentially speaking, there are some rules that can help reduce your workload. Let's see what we've got.
Section B, Rules of Exponents.
We can do a lot of things with exponents, and we've got some rules that'll help us figure out how they work. As we go through the rules, we're going to look at them in letter form first, and then plug in some numbers. Don't worry about having the alphabet mixed in with your math. The letters in these rules are just stand-ins until we stick in some numbers. They're just there to help you learn the rule.
Let's look at the first rule, which shows us how to multiply with exponents. We can use it when our exponents are the same for both base numbers that we're multiplying. To use it, just multiply the bases and keep the same exponent. Here's how the mathematicians write it.
If we're multiplying two numbers, a and b, and the exponent n is the same for both numbers, we simply multiply a times b and keep the same exponent n. So if we're multiplying 3 to the 5th power and 4 to the 5th power, the 3 is our a and 4 is our b, while our n equals 5. That means we just multiply the 3 times 4, which is 12, and use the same exponent 5. So 3 to the 5th power times 4 to the 5th power becomes 12 to the 5th power. Easy, right?
Now, before we go on, just a few words of wisdom, like your grandmother would give you. If we see something raised to the 2nd power, we say that it's squared. And if we see something raised to the 3rd power, we say that it's cubed. This is the way you're most likely to hear it, and it's an impressive way of putting it.
If you apply that schnazzy knowledge to our first exponent rule, it looks and reads like this. We've got 6 squared times 4 squared equals 6 times 4, all squared, which equals 24 squared. Multiplying it out, 24 times 24 equals 576.
Okay, let's continue with the rules. The second rule is just like the first, only this time we're going to divide instead of multiply. Check it out.
We use rule number 2 when we're dividing two numbers that have the same exponent n. It states that a to the nth power divided by b to the nth power equals a divided by b to the nth power. So here, 6 cubed divided by 2 cubed would equal 6 divided by 2, all cubed, or 3 cubed. We simply divide the base numbers and use the common exponent. Then, if we multiplied our answer out, we'd have 3 times 3 times 3, which equals 27.
Rule number 3 is a little different from the others. He kind of went his own way. He's a savvy guy. Rule 3 says if we've got a base number raised to a power and the whole exponential term is raised to another power, then we can multiply the two exponents. Take a look at this.
See how we've got a to the n, which is then raised to the m. Notice how we use parentheses here to raise the number to another power. Let's say we've got these numbers plugged in there, 2 cubed, then all of that squared. If we didn't have the rule, we would do what was inside the parentheses first, giving us something like 2 times 2 times 2 equals 8. Then we have 8 squared, which equals 8 times 8, or 64. But just like the other rules, this one is here to help us shorten the process.
Rule 3 says we can multiply our exponents, n and m. So we take 2 cubed squared and multiply the exponents. Keeping the base number the same, it then becomes 2 to the 3 times 2 power, or 2 to the 6th power. When we multiply it out, we get 2 times 2 times 2 times 2 times 2 times 2, which equals 64.
We're over the hump. Just 2 more rules to go. Let's take a look at number 4. This one says when we're multiplying integers with different exponents and the base numbers are the same, we can just add the exponents and use the common base number. Check it out.
Number 4 is written like this, with a to the nth power times a to the mth power equals a to the n plus m. Here's an example. Notice that with 2 cubed times 2 to the 5th, each has a base of 2. So we keep the base number 2 and add the exponents 3 and 5 together. This gives us 2 to the 8th power, and 2 to the 8th power, when we multiply it out, equals 256.
Okay, the final rule is much like the one we just did, except this time we're dividing and subtracting. Take a look at how it breaks down.
We've got a to the nth power divided by a to the mth power equals a to the n minus m. So, if we have 4 to the 5th power divided by 4 cubed, we keep the base number 4, and this time we subtract the bottom exponent from the top exponent. Subtracting 5 minus 3 gives us 2. So now we've got 4 squared. Multiplied out, 4 squared is 4 times 4, or 16.
Now listen up out there, because we're going to give you 2 more hot tips. You might have noticed in these formulas, multiplication and addition go together, and division and subtraction go together. Associating the two might help you remember how the rules work. That's the first hot tip. The second hot tip is you can always check your work just by multiplying the exponents out the long way.
Believe us, checking is a really good idea. We're going to go through one with you right now so you know just how it's done.
Remember, the first rule is a shortcut that allows us to multiply the base numbers and use the common exponent. Well, this is the simplified version. We use it because it's a time saver, and there's less chance of error if we don't have to write everything out the long way. But if we want to check our work, and who doesn't these days, we can always use the longer way. So let's do one the short way, then check it by using the long way. Take a look.
Say we've got an a value of 2, a b value of 3, and an n value of 2. The shortened version gives us the quantity 2 times 3, all squared, which equals 6 squared, which equals 36. Now we can check to see if we did it right by working it out the long way. When we do, we get 2 squared times 3 squared. 2 squared equals 4, and 3 squared equals 9. Next, we multiply these together and get 4 times 9 equals 36. Notice that our check works out, so we know we did it right.
Now at this point, you may be asking yourself some questions.
Why am I here? What is knowledge? Is there such thing as a negative exponent?
Actually, there is such a thing as a negative exponent. When some people see a negative exponent, they run the other way.
Now, there's no reason to run. They're really not that difficult. All we got to do with negative exponents is take the reciprocal of the base number and make the exponent positive.
The reciprocal?
The reciprocal. The reciprocal of a number is just 1 divided by that number. For example, the reciprocal of the number 6 is 1 over 6, and the reciprocal of 3 is 1 over 3. So let's take a look at how we use the reciprocal to make negative exponents positive.
If we're talking letters, we're going to see it written like this. A to the negative nth power equals 1 over a to the positive nth power. That means if we have something like 2 to the negative 3 power and we want to make our exponent positive, we simply place a 1 over the base number 2 and make the exponent -3 positive. This gives us 1 divided by 2 cubed.
If we have 4 to the -6th power, we convert it to 1 over 4 to the +6th power.
Likewise, 5 to the -2 power becomes 1 over 5 squared. All we have to do to get rid of the negative exponent is take the reciprocal of the base number and make the exponent positive.
Now, the cool thing about having negative exponents is we can still use all the rules we just learned because they still hold true. We can choose to use the short version or the longer version. We'll show you both.
Let's do the short one first. If we look at Rule 1 and plug in the numbers 2 to the -3rd power times 5 to the -3rd power, first we multiply our base numbers to get an answer of 10. Then we use the common exponent, -3, and we've got 10 to the -3rd power. Notice how we still have our negative exponent. We know that 10 to the -3rd power can be made positive by placing 1 over 10 and making the 3 positive. So, now we've got 1 over 10 cubed, which equals 1 over 1,000.
Now we're going to do that same problem, but this time we'll use the longer version and we'll make our exponents positive before we multiply. We're doing it this way so you can see there's more than one way to do them and so you can figure out which works best for you.
This time we've got the longer formula, but we plug in the same numbers from before. So we've got 2 to the -3rd power times 5 to the -3rd power. This time we're going to make the exponents positive before we work it out. So for the first term, 2 to the -3rd, we take the reciprocal of the base number 2 and make the exponent positive to get 1 over 2 cubed. 5 to the -3rd power becomes 1 over 5 cubed. Now we can multiply these out and get 1 over 8 times 1 over 125. When we multiply these together, we get 1 over 1,000. Notice this is the same answer we got when we did it the other way.
All right, see how we can get to the same place by going 2 different ways? It's good to figure out which way you're most comfortable with, because then you won't sweat so much when you take your tests.
We're through the bulk of the exponent rules, but there are a few more that'll help keep your life simple.
Anytime you see a non-zero number raised to the 0 power, this equals 1.
So, 3 to the 0 power, 6 to the 0 power, 1,300,000 and 2 to the 0 power, they're all equal to 1. Any non-zero number raised to the 0 power equals 1. You may also see it written like this: n to the 0 equals 1. Here's one more easy rule.
Any non-zero number raised to the first power equals itself.
So, in other words, 2 to the first power equals 2, 3 to the first power equals 3, 4 to the first power equals 4, taco salad to the first power equals taco salad. However, taco salad to the 0 power equals 1.
All right, we've got a quick recap of the rules for integer exponents. So sit back, relax, grab your pencil, and open your noggin.
The first exponent rule allows us to multiply two numbers together and use the common exponent when that exponent is the same for both base numbers. The second rule is similar to the first, except we use it when we're dividing. We can divide two numbers and use the common exponent when the base numbers share the same exponent. Rule 3 says if we have a base number raised to a power inside of parentheses and then raised to another power outside those parentheses, we keep the same base number and multiply the two exponents.
Rule 4 says if we're multiplying two numbers with common bases, then we use the common base number and add the exponents. Rule 5 says if we're dividing two numbers with common bases, then we use the common base number and subtract the bottom exponent from the top exponent. Now, if we have a negative exponent, we make it positive by taking the reciprocal of our base number.
And the last two rules state that any non-zero number raised to the 0 power equals 1, and any number raised to the first power equals itself.
Now, before we move on, one last thing.
Some teachers will allow you to keep your answer with the exponents in, but other ones will want you to multiply them out. Teachers will also have different rules about when and if you can use calculators. Some teachers will even teach you the conga line in class. So always make sure you pay attention to your teacher.
Part 2, Prime Factorization.
Section A, Factoring.
Factors are two numbers that when multiplied together give you another number. Like 2 and 3 are factors of 6 because 2 times 3 equals 6. And 4 and 5 are factors of 20 because when you multiply them together they equal 20. 2 and 10 would also be factors of 20. So would 1 and 20.
Now sometimes we're given a particular number and asked to list the factors of that number. So we're going to go through an example and show you how that works. Take a look.
If we're going to factor the number 36, we can start with the 1 because it's a factor of every number except 0. We know that 1 times 36 equals 36, so 36 will be the second factor we list right here. Now the process becomes kind of hit or miss, so let's go in a logical order and try the number 2. 2 is a factor of 36 because it divides evenly into 36. So what number do we multiply 2 by to get 36? The answer is 18. That means 18 is another factor, and we put it right here.
See how we're working towards the middle? Next, is 3 a factor? Well, 3 multiplied by 12 equals 36, so 3 and 12 are both factors. 4 times 9 equals 36, so they are both factors. 5 doesn't make the grade because we can't multiply it by any whole number to equal 36. 6 multiplied by 6 equals 36. So we list it as a factor one time, right here. We don't need to write it twice because all we're doing by putting it in this list is saying that it's a factor.
Since 6 times itself equals 36, we know we're done with our factoring because there's no whole number between 6 and 6. Lining it up this way, we can see all the factors of 36. 1, 2, 3, 4, 6, 9, 12, 18, and 36, laid out in sequential order. Let's try one more of these, using the number 18.
As always, we start with 1, and we see that 1 times 18 equals 18. So these are both factors. Is 2 a factor? Well, 2 times 9 equals 18, so both of these are factors. How about 3? 3 is also a factor, because 3 times 6 equals 18. 4 isn't a factor, and neither is 5, because we can't multiply them by any other whole numbers to get 18. Now we know we've found all possible factors because we've already used 6, and there are no whole numbers between 3 and 6 that work.
These numbers we just factored are examples of something called composite numbers. That means they have more than 2 factors. For example, the number 20 is composite because it has 6 factors: 1, 2, 4, 5, 10, and 20. But don't get caught thinking all numbers have many factors. There's another kind of number that actually has only 2 factors total. These numbers are called prime numbers.
A prime number is a number that only has 2 factors, 1 and itself. For example, 7 is a prime number because it only has 2 factors, 1 and 7. No other 2 positive integers can be multiplied together to give us the number 7. Same thing with 13. The only 2 positive integers we can multiply to equal 13 are 1 and 13. 5, 17, and 19 are also prime numbers.
Now, take note that the number 1 is a special case because it's neither prime nor composite. 1 only has 1 factor, which is itself. So the only factor of 1 is 1, and by definition, a prime number must have 2 factors, 1 and itself.
So the difference between prime and composite numbers is that prime numbers have only 2 factors, and composite numbers have more than 2 factors. Got that? Now there are times when you'll need to know which numbers are prime and which are composite.
Back in the 3rd century BC, there lived a man of invention named Eratosthenes. They called him the second Plato. They even nicknamed him Beta because it means second. Eratosthenes calculated the Earth's circumference by paying attention to the Earth's shadows and using simple geometry. Modern-day accounts show he calculated the circumference of the Earth accurately to within 1%. He was also a librarian and invented a way to pinpoint all prime numbers. This guy was smart.
Eratosthenes created a sieve, like this one. Except with his, we can figure out all the prime numbers less than a certain designated number. The sieve is like a filtering system that eliminates all of the numbers that aren't prime and leaves us with the ones we want. Let's use the sieve to figure out all prime numbers less than 100.
Our first step is to figure out all of the prime numbers less than the square root of 100. If you don't know about square roots yet, don't worry too much about it right now. We're going to look at that more in the next section. For now, just know that the square root of 100 equals 10.
So what are all the prime numbers under 10? We've got 2, 3, 5, and 7. Remember, we know this because each of these numbers has only 2 factors, 1 and itself.
Next, we need to write out all of the numbers from 1 to 100 like this. Now we figure out all of the multiples of 2, 3, 5, and 7 that are less than 100 and cross them off. For example, the multiples of 7 are 14, 21, 28, 35, 42, 49, 56, 63, 70, 77, 84, 91, and 98. So we got to cross them all out. We do the same thing for the multiples of 2, 3, and 5, and we get a sieve that looks like this. All of the remaining numbers that are not crossed off are the prime numbers less than 100. So, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, and 97 are the primes less than 100. And that's how the sieve of Eratosthenes works.
Remember, too, that the sieve works with any whole number you want. So if we wanted to find all the prime numbers under 225, we'd just choose that as our starting number and follow the same steps.
It's important to know what the prime numbers are, especially the first 5 or 6, because we're going to be using them throughout our next section for factoring. And you'll most likely be using them throughout your math courses. So you might want to do the sieve a couple of times to really get them down.
Sure, it'd be easier if we just told you, but you need the math practice.
All right, let's take a look at the next section. We're going to be delving into the wild and woody world of arboriculture. That's the study of trees. Why don't you jot that down for your SATs?
Section B, tree diagrams and prime factorization.
We're about to use tree diagrams to get smart about prime numbers. Tree diagrams help us break big composite numbers down into the product of smaller prime numbers with exponents.
We call them tree diagrams because they sort of look like little trees with branches, except they have numbers on them. We start at the top of the tree with a big composite number and work our way down the branches, getting smaller and smaller until we have merely twigs with prime numbers. Check it out.
Say we've got the composite number 72, and we factor it down to 12 and 6. We can't go home yet because these numbers are also composite, and we got to factor until we've got all prime numbers. So, 12 will factor into 4 times 3, and 6 factors into 2 times 3. Then our 4 factors down even further into 2 times 2. So now we've got 2 times 2 times 3 times 2 times 3. Notice we're now at the point where we have all prime numbers. The next step is to express those numbers exponentially. In other words, to write them as base numbers with exponents. Since we have 3 2's, that gives us 2 to the 3rd power, or 2 cubed. And we have 2 3's, so we have 3 squared. That means the prime factorization of 72 equals 2 cubed times 3 squared.
Now, how do we know to start with 12 and 6 in that last example? Well, we could have started with 8 and 9, which are also 2 factors of 72, and gotten the same answer. It's not important which 2 factors of 72 we start with, only that we get started. Once we complete the factor tree, if we did it right, we'll get the same prime factorization either way.
So our goal is to get big composite numbers factored down into a product of prime numbers with exponents. Let's give it another go. Check out the tree diagram for the number 81.
If we factor 81 using the tree diagram, we start with the factors 9 times 9. Notice these aren't prime numbers, so we've got to keep going. Since 9 can be factored into 3 times 3, we get 3 times 3 times 3 times 3, or 3 to the 4th power. If we multiply it out, we see that 3 to the 4th power equals 81, which means we factored correctly, because 81 is our original number.
Now let's try a big scary number like 336. With a big scary number like this, if it's an even number, the easiest thing to do is just keep dividing by 2 until we can't anymore.
Dividing by 2, we see that 2 goes into 336 168 times. So, our first 2 branches are 2 and 168. Now, we can break 168 into 2 times 84. 2 goes into 84 42 times, so these are on our next branches. 42 can be broken into 2 times 21. Now, notice that 2 doesn't divide into 21 evenly, but we can still break 21 down into smaller numbers. We know that 7 times 3 equals 21, so we factor it by breaking it down to 7 times 3. neither 7 nor 3 can be broken down any further because they're both prime numbers. That's good. It's what we want. But we're not done just yet. You see all those 2's? We can't forget about them. They're still part of our prime factorization, so we gotta include all 4 of them in our answer. When we do, the ultimate prime factorization of 336 is 2 to the 4th power times 3 times 7. If we want to check our work, we can multiply this out to get 2 times 2 times 2 times 2 times 3 times 7 equals 336. Since our numbers equal 336, we know we did it correctly. Now, our big scary 336 isn't really that big or that scary.
With the prime factorization of a composite number, you've got to get all the way down to the nitty-gritty of it. You're only finished once you've got all prime numbers and you've given them the right exponents.
Okay, now that we know how to find all the factors of a composite number and how to find prime numbers, let's step it up a notch.
Section C, the greatest common factor.
The best way to introduce the greatest common factor is to pick a couple numbers and factor them like we've been doing. The greatest common factor is going to be the factor with the highest value, or largest quantity, that appears in both lists of factors. Let's try this with the numbers 15 and 20.
Our first step is to factor both our numbers. We're going to do the listing method this time, so let's list the factors of 15 and 20. The factors of 15 are 1, 3, 5, and 15. And the factors of 20 are 1, 2, 4, 5, 10, and 20. The next step in finding the greatest common factor is to figure out all the factors that these two numbers have in common. In this case, we notice that 1 and 5 are in both lists, so they're called common factors. Now remember, the greatest common factor is the one out of these two that has the highest value. In this case, the greatest common factor is 5 because it's a common factor of 15 and 20, and it's greater than the other common factor, 1.
Another thing to know about the GCF is that it's possible the GCF of two numbers will equal 1.
For example, with the numbers 7 and 15, 1 is the greatest common factor because after we factor them out, we see that 7 and 15 have no other factors in common. So, 1 is both their only common factor and their greatest common factor.
Since we found the GCF in our previous examples by listing factors, now we're going to try another way. Remember way back about 3 minutes ago? We used the tree diagrams to do prime factorization. Well, we're going to use that same prime factorization stuff to help us find the GCF another way. Let's take a look.
Say we're searching for the GCF of 12, 28, and 48. First, we're going to factor them down to prime numbers using the tree diagram, and then put them into numbers with exponents. So, starting with 12, 12 breaks down to 6 times 2, which further breaks into 3 times 2 times 2, or 3 times 2 squared. 28 equals 14 times 2, which breaks into 7 times 2 times 2, or 7 times 2 squared. And 48 equals 12 times 4, which breaks into 4 times 3 times 2 times 2, which equals 2 times 2 times 3 times 2 times 2, or 2 to the 4th power times 3. Now let's figure out the GCF.
After we get the prime factorization, we've got to look at the numbers and their exponents and figure out which will be a part of the GCF. Any prime factor we choose for our GCF must be a factor of all 3 of the original numbers because that's what makes it a common factor. So, when we look at the prime factors, we see that 2 is the only one that's a factor of all 3 numbers. So it's going to be the lone base number in our answer. The only thing left is to figure out what exponent 2 will have.
When deciding on the exponent, we look at the exponents for each of the 2's. We've got 2, 2, and 4. To get the GCF, we just take the smallest exponent. So in this case, we would use 2 as our exponent. That means our GCF is 2 squared.
So, our GCF, 2 squared, equals 4 when we multiply it out. 4 is the greatest common factor of 12, 28, and 48 when we express the GCF in whole numbers.
A great way to check our work is to list the factors like we did in the first method and see if we got the same answer. See how when we list out the factors in whole numbers, 4 is the GCF. That means we did our factoring correctly.
So, when we're looking for the GCF, first we want to get the prime factorization of our numbers. Then figure out which prime numbers are factors of all our original numbers, and how many times each of those prime numbers is represented. Then, we take the smallest exponent, and we've got our GCF. Now we're going to take a look at something that's kind of like the cousin of the GCF, but with its own identity.
Section D, the least common multiple.
Before we get into the least common multiple, or LCM, let's take a minute and talk about what a plain old multiple is. A plain old multiple is what you get when you multiply one number by another number.
All right, let's take the number 3. What are its multiples? Well, 1 times 3 equals 3. 2 times 3 equals 6. 3 times 3 equals 9. 4 times 3 equals 12. 5 times 3 equals 15. 6 times 3 equals 18. 7 times 3 equals 21. And 8 times 3 equals 24. So the first 8 multiples of 3 are 3, 6, 9, 12, 15, 18, 21, and 24.
And now, it's the artist formerly known as the least common multiple. Give it up for the LCM. To find him, just look in a few lists of multiples. He's the number with the smallest numerical value that appears in all your lists. Take a look.
These are some multiples of the numbers 6, 10, and 15. What we want to do is figure out the least common multiple of all three. So, the LCM is the multiple that 6, 10, and 15 all have in common and has the smallest numerical value. You might notice that 60 is a multiple in all three lists, but so is 30. Because we're smart, we know that 30 is smaller than 60, and 30 is the smallest multiple they all have in common, which means 30 is the LCM of 6, 10, and 15.
When you're listing multiples, the fastest way to find the least common multiple is to look at the multiples of the largest of the numbers. So, for our previous example, to find the LCM of 6, 10, and 15, 15 is the largest number, so you would look to the multiples of 15. First, try 1 times 15, or 15. 15 is not a multiple of 6 and 10, so next try 2 times 15, or 30. 30 is a multiple of both 6 and 10, as well as 15, so our number is 30.
Listing multiples, like we just did, is one way of finding the least common multiple, but there is another way to do it. Any guesses?
Look in the back of the book.
Nice, but no. We're going to use the prime factorization method. Let's use the same numbers, 6, 10, and 15. Now remember way back about 2 minutes ago when we found the GCF? Well, our first step here is the same. We're going to factor with tree diagrams and then give our prime numbers exponents.
So, if we take 6, we get the prime factors 2 times 3. 10 breaks down to 5 times 2, and 15 gets mapped out so that its prime factorization is 5 times 3.
Now we've got all our prime factors and we need to express them with exponents. This part is a little different from the greatest common factor. To represent the LCM with prime numbers and exponents, we need to take every prime number that appears as a prime factor and write it once with the biggest exponent that appears. Take a look.
Since the prime numbers we see are 2, 3, and 5, we're going to use each of these one time and give them an exponent. For the LCM, we use the biggest exponent for each prime number that is represented. This is different from the GCF, where we use the smallest. Notice in this example, the most each prime number appears in a single factorization is 1 time. So the biggest exponent we can use for each is 1. That means the LCM of 6, 10, and 15 is 2 to the first power times 3 to the first power times 5 to the first power, or 2 times 3 times 5. See how when we multiply 2 times 3 times 5, it equals 30, which is what we got before when we compared multiples with whole numbers.
Excuse me.
Dude, get the mustard, dude!
When you multiply your prime numbers with exponents, they equal my whole number. I checked it out.
What now, dude?
There's nothing left now but math. Hey, let's get the LCM of 10 and 25.
Doing the prime factorization of 10 and 25, 10 breaks down to 2 times 5, and 25 breaks down into 5 times 5, or 5 squared. At this point, we're already down to our prime numbers, so we want to represent all the prime numbers that appear. In this case, we've got 2 and 5. So what is the most number of times 2 appears in a single factoring? Well, it's just 1 time. That means our exponent for 2 is 1. What about 5? The most 5 appears in a single factoring is 2 times, so 2 is our exponent for 5. That means the LCM of 10 and 25 is 2 times 5 squared. If we multiply the LCM out, we get 2 times 5, which equals 50. And remember, we can check the LCM by listing the multiples out this way. And here we see that 50 checks out as the LCM.
Ta-da! So that's how we find the LCM. We do the prime factorization of our numbers, then represent all prime numbers with their highest exponents. Now fancy this. It's already time for a review of this section. So sit back and absorb.
Factors are 2 numbers that, when multiplied together, give you another number. A composite number has more than 2 factors, while a prime number has only 2 factors, 1 and itself. When we look for the prime factorization of numbers, we can use tree diagrams to break a composite number down into the product of smaller prime numbers. If we're looking for the GCF of a set of numbers, we do the prime factorization for each of the numbers. Then notice which prime numbers appear as factors of all numbers. We take those prime numbers and represent them with their smallest exponents. This gives us the greatest common factor between our factored numbers. If we're looking for the LCM for a set of numbers, we need to represent every prime number, and we need to represent it with the biggest exponent it has in one factorization. This will give us the least common multiple in our set of numbers.
Okay, now that we got all that tree and factoring stuff down, we can swing our shovels over our shoulders and get ready to start digging. Welcome to...
Part 3, Roots.
In this section, we're going to talk about squaring numbers as well as finding square roots and other higher roots. But before we get there, we've got to take a little detour and talk about absolute values. Let's get started with that.
Section A, absolute value.
One way to understand the absolute value is to imagine a number line. If you have one in front of you, it's even better. When we've got a number line, we can figure out how many units away from 0 our number is, and this is what the absolute value is all about. Check this out.
If we're asked to find the absolute value of 5, we see here that it would be 5 units from 0 on a number line. That means the absolute value of 5 is 5. We see it written like this. Those straight lines on each side of the 5 mean absolute value. Likewise, the absolute value of -5 would also be 5, because -5 is also 5 units away from 0.
There's no such thing as a negative absolute value. It is always positive, or 0. We're simply counting the number of units that a particular number is away from 0. So the absolute value of 0 is 0, and the absolute value of any non-zero number is always positive.
So the absolute value of -3 is 3. The absolute value of 804,329 is 804,329. And remember, the absolute value of 0 is 0.
Woohoo! Now that we've got absolute values pegged down, let's go for squares.
Section B, squares and square roots. In this section, we're going to take a look at the expansive world of roots. There are many different types of roots, but we're going to start with square ones and work our way up.
Back at the beginning of the tape, we talked about the square of a number. Remember when we see something like 9 squared or 7 squared, that means we multiply the base 2 times. So 9 squared equals 9 times 9, or 81. And 7 squared equals 7 times 7, or 49. Well, finding the square root is just like doing the opposite of finding the square. Check it out.
See how 9 squared equals 81? Well, that means the square root of 81 is 9. Same thing with 7. 7 squared equals 49, so the square root of 49 equals 7. The square root of a number is simply the original number we multiplied 2 times. We use this symbol here to mean square root. It's called the radical.
This just in, the radical means we take the square root of a number. The number underneath the radical is called the radicand, and the whole kit and caboodle is called the radical expression. Let's go now to Carrie Curtis live on MathCam for more. Carrie.
That's right, Ralph. And we've been out here all day asking people that one key question. What do you do with the radical once you found the square root? Here's what they had to say.
When you find a square root, you just chuck it.
You heard it here first, folks. When you find the square root, you just chuck the radical. I'm Ralph Newsman. Good night.
So if we saw the number 25 under a radical, that means we want the square root of 25. Well, what number multiplied 2 times equals 25? The answer is 5, so 5 is the square root of 25. We express this by writing a plain 5 and getting rid of the radical.
Now in the math community, or in one of your books, you might see a formula with some letters in it to explain the square root. Let's see what it looks like so it won't catch you off guard.
If you come across this, the number c is the square root of a if c squared equals a. Don't worry, this is just the letter version of what we've been doing with numbers. See how it works if we substitute the number 36 for a? Now what number multiplied 2 times equals 36? We figure out that c equals 6, because we know that 6 times 6 equals 36.
Okay, now that we've got that down, in this jungle of roots, there's something else we've got to look out for. We know the square root of 36 is 6 because 6 times 6 equals 36. But negative 6 times negative 6 also equals 36 because 2 negatives multiplied together equal a positive. This means that negative 6 is also a square root of 36. Let's look at this in more detail.
So how do I know when to give the negative answer or the positive answer?
Well, there's just a little something you got to watch out for. You got to pay attention to the way things are written.
When we see a radical sign, just a plain old granolo natural no frills radical sign, it means we're looking for the positive square root of that number. See here, the square root of 9 is 3. Easy, right?
Now, if we want the negative root of a number, we'll see it written like this, with a negative sign in front of the radical. Not under the radical, but in front of it. This means we want the negative square root of 9, which equals negative 3.
So when we've got that negative sign in front of our radical, that's when we want the negative root.
Now, so far, all the numbers we've been considering have not only been squares, but also perfect squares. A perfect square is a number that has an integer square root. For example, some of the perfect squares are 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. They're perfect squares because their roots are integers.
The square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. The negative square root of 16 is negative 4.
Now, these are all integers or whole numbers, which when multiplied twice equal other whole numbers. They're not decimals or fractions. This is why they're considered perfect squares.
But in this imperfect world, it's also possible to have squares that aren't perfect.
Take the square root of 18, for example. 18 is not a perfect square because no integer times itself equals 18. So let's try something a little tricky here. We're going to break this thing down to try and find some factors of 18 that might actually be perfect squares. Our first step in this process is to think of some factors of 18.
How about 6 and 3?
Well, yes, these are factors, but neither of them are perfect squares, so that doesn't really help us. But look at the factors 9 times 2. We know that 9 is a perfect square that has a square root of 3, so this is good stuff. These are the factors we want to use. Now, instead of 18 under the radical, we can make it 9 times 2. Then we can take the square root of 9. Remember, we express this by taking the 3 out from under the radical sign, giving us something that looks like this. 3 times the square root of 2. Why can we do that? Well, since 9 is a perfect square, we can take the square root of that factor, which is 3, and bring it outside the radical. This is how we end up with 3 times the square root of 2.
Now, technically, we can find the square root of 2 by writing it as an ugly-looking decimal. But for right now, we're going to leave that 2 under the radical sign because it's not a perfect square. So our final answer would be 3 times the square root of 2.
Now, just like we wouldn't win a gold medal in the Great Pancake Bake-Off if we never practiced making pancakes, we've got to practice our skills with non-perfect squares to make sure we've got them down. So let's do a few more.
How about 120? That's a nice, hearty number. If we've got the square root of 120, we can factor it down to the square root of 12 times 10. Well, 12 can be broken down to 4 times 3, and 10 can be factored into 5 times 2. So we've got the square root of 4 times 3 times 5 times 2.
Since 4 is a perfect square, it can be taken out from under the radical as a 2, giving us 2 times the square root of 3 times 5 times 2. Notice that none of the numbers left under the radical are perfect squares, so we can multiply them back together. When we do this, we've got 2 times the square root of 30. We keep our answer at 2 times the square root of 30 because 30 is not a perfect square and doesn't have any factors that are perfect squares.
Okay, you wake up to find the square root of 72 hanging like a mobile from your ceiling. Immediately you stare it down because you know how to deal with it. You say,
72. I know what to do this time. Advantage. Mine.
The square root of 72 can be broken down to the square root of 12 times 6, which can be factored to the square root of 3 times 4 times 3 times 2. Now we can remove a 2 from under the radical because 2 is the square root of 4. Yeah! But, aha, this time I noticed that we're left with 2 times the square root of 3 times 3 times 2. See how 3 times 3 equals 9? That means 9 is a perfect square. So we take the square root of 9, which is 3, by placing that 3 outside the radical. Now we've got 2 times 3 times the square root of 2. Well, we can multiply our integers 2 times 3 to get 6, and we end up with an answer of 6 times the square root of 2. Yeah!
Nice work. Remember, squares and square roots are a very important part of algebra. So if you think you missed something or just aren't sure about how they work, now might be a good time to rewind the tape and check it out again. You'll need to use the concepts in order to get the next section. But if you're ready, let's move on and tackle higher roots.
Section C, higher roots.
Most of what we've talked about so far has revolved around the square roots, but they're not the only roots of this earth. There are such things as cube roots, fourth roots, fifth roots, caret roots, family roots, tree roots. When we talk about any number roots greater than square roots, we stick them all under the umbrella of higher roots.
Let's start with the first higher root, the cube root. Remember that when we have a number cubed, for example 4 cubed, it means 4 times 4 times 4. When we cube a number, we multiply that number 3 times.
A cube root, then, is just like a square root, except this time we're looking for a number multiplied 3 times to get another whole number. See that little 3? We say that 3 is in the arm of the radical, and it signals to us that we're looking for the cube root. An example is the cube root of 729, which equals 9, because 9 times 9 times 9 equals 729.
Take a look at the cube root of 8. Now, what number multiplied 3 times equals 8? The answer is 2, because 2 times 2 times 2 equals 8.
Similarly, the cube root of 27 equals 3, because 3 times 3 times 3 equals 27.
Now, cube roots are different from square roots because when you've got a cube root, you're dealing with 3 numbers, and when you have a square root, you're dealing with 2. This can affect your answer if you've got negative numbers, so make room in your mental duffel bag for the following information.
Whenever we have a cube root or some other odd root, it's possible for us to end up with a negative number under the radical. This is because whenever we multiply an odd number of negative integers together, our answer is negative. Take a look at this.
If we have negative 2 times negative 2 times negative 2, we get negative 8. So, if we're asked to find the cube root of negative 8, we know that the answer is negative 2.
Now, notice how this is different than when we work with even roots. Whenever we multiply an even number of negative integers together, our answer will be positive.
If we multiply negative 2 times negative 2, we get positive 4. Because a negative times a negative always equals a positive. So in our travels, if we come across a negative number under the radical and we're looking for an even root, like the square root of negative 4, we're going to say that it's undefined.
It's undefined.
It may sound a little confusing, but it's not that bad once you do a couple of them. So let's go through it one more time.
If we're looking for an odd root of a negative number, like the cube root of negative 27, we can say that the answer is negative 3. This is because -3 times -3 times -3 equals -27. Now, if we're given a negative number and asked to find an even root, like the square root of -16, we're going to say that it's undefined. The reason we say it's undefined is because we can't find one real number multiplied 2 times to equal -16.
Now there's one more teeny tiny piece to this whole positive-negative bit. Remember earlier in the section we talked about the negative square root of a number? Well, this is altogether different than the square root of a negative number. The good thing is that it's easy to tell which one we're looking for by where the negative sign is. Take a look.
Notice how the negative sign in this case is underneath the radical sign. This means we're looking for the square root of -16, which we say is undefined. But this is different than when we have a negative sign in front of our radical. Remember that this means we're looking for the negative of the square root of a number, which we can do for any number. So here, the negative square root of 16 is -4.
Okay, let's get away from negatives for a while and go forward to one more higher root. So far, we've looked in depth at square roots, then cube roots. Now let's check out an example of the fourth root.
Raising a number to the fourth means multiplying that number 4 times. So saying the fourth root of something means finding the number that when multiplied 4 times gives us a particular number. For example, the fourth root of 16 equals 2, because 2 times 2 times 2 times 2 equals 16. Likewise, the fourth root of 81 equals 3, because 3 times 3 times 3 times 3 equals 81.
Following that pattern, we can find the 27th root of a number, which would be the number that when multiplied a total of 27 times gives us our original number.
Of course, the chance anyone will ask you to find the 27th root of a number is about as likely as someone asking you to build a house out of bubblegum and tinfoil. But hey, it could happen.
Okay, it's that time again, folks. We've come to the end of the section. Please make sure that your seat is in the full upright position, with your safety belt fastened, your mind open, and your infrared review goggles on.
Remember, the absolute value of a number is always the positive value of that number. Or if we've got 0, the absolute value is always 0. To find the square root of a number, look for 2 identical factors. Since the square of 12 is 144, then the square root of 144 is 12. Remember that after we get the square root of a number, or any root, we take it out from under the radical sign.
And if we see a bigger number in the arm of the radical sign, then we're looking for a higher root. So if we see a 6 in the arm of a radical, we're looking for a number when multiplied 6 times gives us the number under the radical. If we catch an even root with a negative number under the radical sign, we say it's undefined. But a negative number with an odd root is okay. Now, this is altogether different than taking the negative root of a number, which we can always do when we see the negative in front of the radical.
Now that you've got the skinny on roots, you're prepared for a new mission. We're going to explore the world of fractional exponents, piece by fractional piece.
Part 4, Expressing Roots with Fractional Exponents.
Section A, Fractional Exponents.
Sometimes when you're dealing in the realm of exponents, they come to you in the form of fractions. When this happens, you gotta know how to deal with them head on and show them who's boss. Here's how.
We're going to prepare ourselves by taking a look at the formulas for fractional exponents, because they'll be a good tool for us to do battle with. So, let's take a look at these letters, then we'll stick in some numbers.
The first form for fractional exponents looks like this. A base number a raised to the 1 over n power, where n is a positive number. So, we might have something like 3 to the 1/2 power. When we've got a number with an exponent that's a simple fraction, like 3 to the 1/2 power, it just means the square root of 3. We look at what number is in the denominator and take that root of our base number.
So, in the same way, 3 to the 1/3 power means the cube root of 3. 3 to the 1/4 power means the 4th root of 3. 3 to the 1/5 power means the 5th root of 3, and so on.
Now, what happens if we've got the same kind of exponent, except now it's negative? Well, we've got to do things just a little different. We've got to take the reciprocal of the base number and then make the exponent positive.
The reciprocal of a number is 1 over that number. The reciprocal of 5 is 1 over 5. Check out this next item.
Let's say we have 8 to the negative 1/3 power. The rule says we can take the reciprocal of the base number, giving us 1 over 8, and make the exponent positive. So we get 1 over 8 to the positive 1/3. We know that the 1/3 power also means the cube root, so we get 1 over the cube root of 8. But we're not quite done because we can take the cube root of 8 and simplify it to 2. So, when all is said and done, we've got 1 over 2, or 1/2.
So, we just want to take the reciprocal of our base number and make the exponent positive. Then we simplify it if it's necessary. Let's do a couple more for practice.
If we've got 3 to the negative 1/2, first we take the reciprocal of the base number by placing 1 over 3. Next we make the exponent positive. Now we've got 1 over 3 to the positive 1/2 power. Again, because we've got a 2 in the denominator of our exponent, we take the square root of our 3 here. So we end up with 1 over the square root of 3. Since the square root of 3 is not a perfect square, we just leave this as our answer.
Finally, if we look at 2 to the negative 1/3 power, our first move is to take the reciprocal to get 1 over 2. Then we make the exponent positive, and we've got 1 over 2 to the positive 1/3 power. Next, we take the cube root of our bottom number, 2. So, our answer is 1 over the cube root of 2.
Notice anything similar in all the exponents we've done so far? They've all had 1 in the numerator. That makes a pretty clean deal. But what if we had a numerator where the number was something other than 1? What do you do?
Well, when we have a fractional exponent where the numerator is not a 1, we have 2 easy steps. We raise the base number to the power of the numerator and then take the root as signaled by the denominator.
Requesting permission to raise the base number to the numerator. That's the base number to numerator. Come in, ground.
Roger, base. We are now raising you to the numerator. You are now fully raised. Just waiting now on the denominator. The denominator should transform into the root at any moment now. Oh, there it goes. There it goes, ladies and gentlemen. The denominator has signaled which root and...
Ground, can we go over that again?
Roger.
Roger. Let's look at that again. Say we have a number like 4 to the 3/5 power. Now stay with me here. The numerator of the fractional exponent, 3, is going to become the exponent for the base number, 4, so we get 4 to the 3rd power. Notice we replace the 3's spot in the fraction with the number 1. Remember how we learned to use the fraction 1/5 to take the 5th root? So, we do that here and take the 5th root of 4 cubed.
But our answer can still be simplified. See how we've got 3 4's under the radical? Well, we know 4 can be broken down into 2 times 2, so let's do that. When we break our 4's down, we've got 6 2's under the radical. Now, we're ready to take the 5th root, which means we take a single 2 and bring it outside the radical, leaving 1 2 underneath. That signifies that we've taken 5 2's from under the radical, or the 5th root. When all is said and done, we're left with 2 times the 5th root of 2.
What if we had 4 to the negative 3/5 power?
Well, if we had 4 to the negative 3/5 power, remember, the only thing we do differently is our first step. We've got to take the reciprocal of the base number first and make the exponent positive. We get the reciprocal by placing 1 over 4 and then make our exponent positive 3/5. Now our steps are the same. We raise our 4 to the 3rd power and take the 5th root of that. Next we simplify, so we've got 1 over the 5th root of 4 times 4 times 4, which breaks into 2 times 2 times 2 times 2 times 2 times 2. Then we take the 5th root, which gives us 1 over 2 times the 5th root of 2.
Let's do one more example where our exponent doesn't have a nice, neat 1 in the numerator. Take a look at 2 to the negative 2/5 power.
Our first step is to take the reciprocal because of the negative exponent. Then we get 1 over 2 to the positive 2/5 power. Next we use the numerator of the exponent, 2, and raise our base, 2, to the 2nd power. Remember when we take that numerator, we put a 1 in its place. Now we take the 5th root of 2 squared, or the 5th root of 4. Since we can't take the 5th root of 4 evenly, we're going to leave it as is. That means our answer is 1 over the 5th root of 4.
So that's how we handle fractional exponents. It's really not that hard to deal with them once we get the rules down. Now let's take a little time to do a playback of part 4, our fun with fractional exponents.
A fractional exponent with the 1 in the numerator means we can take the root of the base number as signaled by the denominator. If we've got a number that isn't a 1 in the numerator, then we have to raise our base number to the numerator and then take the root as signified by our denominator. And finally, if we've got a negative fractional exponent, we take the reciprocal of the base number and proceed with the usual steps. Raise the base to the numerator and use the denominator as the root.
Now that we've done all that good exponent stuff, we're going to look at something a little different. We're going to take a sizable step closer to the world of algebra. Let's go.
Part 5, Inequalities.
All right, when we're talking about inequalities, we're talking about mathematical statements that are unequal. They have two sides that don't balance. So store that away in your brain bank, because before we get into the thick of inequalities, we're going to look at some different kinds of numbers and how they fit on a number line. This will set us up for our work with inequalities.
Section A, Numbers and Number Lines.
If you remember back to the beginning of the tape, we talked about integers like 0, 1, 2, and 3, and negative 1, 2, and 3. And we've also talked about fractions. All these numbers are called rational numbers. What's that? Well, a rational number is just a number that can be expressed in fractional form. 5 is a rational number because it can be expressed as 5 over 1. 17/35 is also a rational number because it's already in fractional form. And now that we know what rational numbers are, the time has come for us to explore new lands.
Just like we have rational people and rational numbers in this world, we've also got irrational ones.
Shibboleth-a-ding-dong! Shibboleth-a-ding-dong!
Irrational numbers are decimals that go on forever and don't repeat.
An example of an irrational number would be the number pi. We often see it listed as this symbol, which is the Greek letter pi. Pi represents the ratio of a circle's circumference to its diameter. But don't worry yourselves with that right now. What we want to focus on is the numerical expression of pi, which is 3.14. We usually use 3.14 as a value for pi, but this is actually rounded off. Pi really goes on and on forever. We just round it off to 3.14. Its decimal representation never ends and it never repeats. That's why it's an irrational number.
Another example of an irrational number is the square root of 2. The square root of any number that is not a perfect square is an irrational number. They're irrational because the decimal representations just keep going and they don't repeat. They just refuse to give up.
Now, there are numbers that go on and do repeat. These are called repeating decimals. A repeating decimal is a rational number. An example is the fraction 1/3. If we tried to divide this out, we'd continue to get 0.33333. Notice the repetition of the 3. This would go on forever. Same with the fraction 23 over 99. If we divided this out, we'd continue to get 0.23232323 forever.
Forever is a long time.
So both a repeating decimal and an irrational number go on forever, but the non-repeating decimal is an irrational number while the repeating decimal is a rational number. Now, a good thing to know about all the numbers we've been talking about so far is that they all fall under the big old heading of real numbers.
I am real. This is real.
That's right. And whenever we've got a real number, we can put it on a number line. We used number lines a little while back in the absolute value section. Remember, a number line looks like what it sounds like it looks like. It's a line with a bunch of ordered numbers. We can use this number line to express certain mathematical statements, or just to identify a particular number.
Whenever we have a number line, 0 marks the division between the positive and negative numbers. All of the positive numbers are to the right of 0, and all of the negative numbers are to the left of 0. The arrows at the end of the lines mean that each end goes on and on forever.
Now here's the freaky thing. Number lines even include irrational numbers. Remember we said the square root of 2 was an irrational number? Well, it still is. And it's easier to figure out where it goes on the number line if you convert it into a decimal first. So you may have a chart in your book or a calculator that shows you the square root of 2 is approximately 1.41 when we round it off.
When we look at it this way, we see that 1.41 is close to 1.5, which is the halfway point between 1 and 2. We usually make an estimate or a guesstimate when we're putting irrational numbers on a number line. So on the number line, the square root of 2 goes just a shade to the left of where we'd find 1.5, and we put a little marker. We need to label the point since it doesn't fall on a whole number. Right here, we're going to write in the square root of 2, so anybody else who looks at our line can know what number we're talking about.
How about a number like 2.5?
We know that 2.5 is midway between the whole numbers 2 and 3 because it just means 2.5. So this is where it goes on the number line, right smack dab in the middle between 2 and 3. Make sense?
Mm-hmm. How about a negative number?
Say we have a negative 3.4. That means we have a number that is smaller than negative 3 and larger than negative 4, which means that our point would go right here on the number line. Notice that negative 3.4 is bigger than negative 4. The numbers to the left are less than the numbers to the right, which means the further left we go, the smaller we get.
It may seem a little funny, but if you're confused, don't call the math helpline just yet. We're going to get into some more details. Let's get into inequalities.
Section B, putting inequalities on the number line.
An inequality is a mathematical expression that is unbalanced. Statements like 5 is greater than 3 or 4 is less than 7 are considered inequalities because the two sides don't balance. Here's an example of what we're talking about.
Suppose you and your friend are on a teeter-totter, and neither of you are pushing with your feet. If your weights are equal, then the teeter-totter would be straight across like this. Now, if your friend got off, you'd go crashing into the ground. Now your weight is greater than the weight on the other side, and that means the teeter-totter is unbalanced.
Now, if your other friend, Big Bruce, decides to come and get on the other side, you're going to go soaring back up. Now the teeter-totter is unbalanced again, but this time it's unbalanced the other way. So, we say that your weight is less than Big Bruce's.
Let's go over the symbols we use when we're working with inequalities. Whenever you see this symbol, it means less than. So if you see something like this, it means 3 is less than 5. It's kind of like an equal sign, except 3 doesn't equal 5, it's less than 5. We use this wedge-shaped symbol to indicate less than. See how when we straighten this wedge out, it looks like the letter L? When you come across the symbol facing this way, you can remember that it looks like an L, which stands for less than. So here, 2 is less than 7.
Now, if you see the symbol facing the other direction, then it means greater than. So this would be read, 6 is greater than 2. Likewise, 9 is greater than 8.
Less than, greater than, less than, greater than, less than, greater than.
Now, you can remember which way to face the symbol if you use this little trick.
Think of your symbol like the mouth of a big, hungry, number-eating dinosaur. Your dinosaur is always going to want to eat the bigger number, even if he's already had lunch. So the dinosaur's mouth will always be going for the bigger number.
Now there's one more little piece to this inequality puzzle. Sometimes the greater than or less than signs can have a line underneath them.
When you see the less than sign with a line under it, it means less than or equal to. If you see the greater than sign with a line under it, it means greater than or equal to.
So when we see something like this, which means 3 is less than or equal to x, or this, 9 is greater than or equal to x, you might be noticing that we really haven't dealt with the x's before. But at this point, just know that these x's here are like the other letters we've seen. They're kind of like stand-ins. They simply represent some number, or numbers, that would fit correctly into our mathematical statement. So in our first inequality, x could have any value higher than 3, or x could equal 3 itself. In our second inequality, x could equal 9, or anything less than 9.
Alrighty then, with that knowledge under our belts, let's talk about intervals. Interval is a word we use when we want to talk about all of the numbers between two other numbers, or greater than one number and less than the other. So, if you see this notation, parentheses 4, comma 8, parentheses, this represents all numbers between 4 and 8.
When dealing with intervals, we come across two different ways they're written. There are parentheses like these, and brackets like these. Each has its own meaning.
Kind of like signs in baseball.
With intervals, the left parentheses means greater than, and the right parentheses means less than. This is called an open interval. If we've got brackets, the left bracket means greater than or equal to, and the right bracket means less than or equal to. This is called a closed interval. The numbers inside these symbols should be separated by a comma. The first example we looked at was the open interval bounded by 4 and 8. We know it's open because it's got parentheses. This can also be written with inequalities like we did before. It looks like this. X is greater than 4 and less than 8. That means we've got the interval of all numbers greater than 4 and less than 8. That X, you see, simply represents the phrase all numbers. Therefore, our interval includes the integers 5, 6, and 7, and all numbers in between, like 5.22 and 6.11. But it doesn't include 4 and 8 themselves.
Now, if we saw this, bracket, 0, 3, bracket, we would know that it meant the interval of all numbers between 0 and 3, including 0 and 3. It can also be written like this, which means x is greater than or equal to 0 and less than or equal to 3.
Now, just like we can go to our closet and slip on one ice skate and one roller skate, we can also mix up brackets and parentheses. Take a look at these dicey combos.
We could come across something that looks like this, bracket 3, 6, parentheses. Now remember that the left bracket means greater than or equal to, and the right parentheses means less than. So our interval would translate into all numbers greater than or equal to 3 and less than 6. Remember, we can also write it this way, with the corresponding symbols and numbers on either side of the X. Okie dokie. I think we're ready to put some of these on a number line.
Say we've got the interval of -2 and +2. Remember, what this really means is all numbers greater than -2 and all numbers less than +2.
This just in. When we put inequalities on number lines, we use an open circle to mean greater than or less than, and a filled-in circle when the interval includes the phrase or equal to. To recap, open circle for greater than or less than, filled-in circle when we've got or equal to. Now, back to our example.
Because we've got an open interval, we put an open circle at -2 and an open circle at +2. We do this because we're only dealing with less than and greater than signs, not equal to. Next, we shade the line in between them. Now, the shaded part of the number line represents our interval between -2 and +2, but not including -2 and +2.
Let's do another one of these. Check out parentheses 0, 3 bracket, or x is greater than 0 and less than or equal to 3.
On the number line, we put an open circle at 0 and a filled-in circle at 3. See, now we've got a closed circle at 3 because we're dealing with a right bracket, which means less than or equal to. Then we shade the line in between them. This means the shaded part of our line represents all the numbers after 0 up to and including 3.
Okay, let's do one more of these puppies just to make sure we're on the same wavelength. Take a look.
We've got bracket -1, +1, parentheses. This means x is greater than or equal to -1 and x is less than +1. It maps out like this. We've got a filled-in circle at -1 and an open circle at +1. The line in between is shaded.
All the intervals we've looked at so far have been what are called finite intervals. They're considered finite because the length of the intervals are finite, meaning we can measure where they begin and where they end. For example, the interval bracket 1, 4 parentheses starts at 1 with a filled-in circle and ends at 4 with an open circle. Notice it starts at the left value and ends at the right value. This means it's a finite interval because it has a start and an end.
Your class periods are finite intervals. A chess match is a finite interval. Finite, beginning and end.
Lo and behold, there's something called an infinite interval. This is an interval that goes on and on and on and on, and we can't measure its length. When we have an interval that goes on and on and on, this is called infinity.
Infinity. So long. So very, very long. It's really long.
The symbol for infinity looks like a number 8 taking a nap. When we talk about infinity, we're usually talking about all numbers greater than or all numbers less than a certain number. Let's look how it's written, and then we'll see how it works on a number line.
When we see this, parentheses n, infinity parentheses, it translates into all numbers greater than n. It can also be written as this inequality. x is greater than n. While n stands for a particular number, that x stands for all numbers. So, we've got all numbers greater than n.
That's so many numbers.
Yep, it's a lot of numbers, but it's easy to deal with. All we gotta do is plug in a number value for n, then we can map it out on a number line. So let's substitute n with the number 4.
Now our interval looks like this. Parentheses, 4, comma, infinity, parentheses. This means all numbers greater than 4. On our number line, we make an open circle at the number 4 and shade the line all the way to the right. Here the numbers start at 4 and go on and on. They never stop like they would in a finite interval.
Likewise, if we saw bracket 9 comma infinity parentheses, this means all numbers greater than or equal to 9. We'd make a filled-in circle at 9 and shade all the way to the right.
What if you had something less than 0?
Well, if we have a problem where we're looking for all x's less than 0, we would write the interval notation like this. This symbol represents negative infinity. In the same way that positive infinity deals with the right-hand side of a number line, negative infinity deals with everything to the left side. For example, if we see this, this means all numbers less than n. N is just a stand-in for a particular number. We could choose a value for that number, let's say -1, and make it parentheses, negative infinity, comma, -1, parentheses. This means all numbers less than -1.
So, if we took the open interval of negative infinity to -1 and put it on a number line, it'd look like this. We've got an open circle at -1, and our line would be shaded all the way to the left. Now our number line represents all the numbers less than -1.
Now, we can even see something as seemingly cryptic as this. But don't worry, it's not Egyptian hieroglyphics. And unfortunately, it's not the recipe for world peace. It's not even the answer to a Final Jeopardy puzzle. But it is the interval that symbolizes all real numbers. Every last one.
To put it on a number line, we simply shade the whole thing all the way through both ends. This represents all real numbers.
So when we're talking about intervals with infinity, we have 5 basic combinations that we come across. Take a peek and see if you remember them all.
All real numbers. All numbers greater than n. All numbers greater than or equal to n. All numbers less than n. All numbers less than or equal to n.
Okay, just a little bit more about number lines and intervals. Back to our old friend, the absolute value. Remember that the absolute value of a number always equals the positive value of that number, or 0. Well, now we're going to put some absolute values on a number line.
Let's say we've got the absolute value of x is less than 3. In this case, we don't know what the value of x is, so our job is to figure out what number or numbers will fit correctly in our inequality if we substitute them in for x. Now, we do know that any value we choose for x has to have an absolute value that's less than 3. That's what our inequality says. So, what are some numbers whose absolute value is less than 3?
Well, any of the numbers from 0 to 3 work because their absolute values are all less than 3. For example, the absolute value of 2 is 2, which is less than 3. So it fits correctly. The same is true for all the numbers in this shaded area. Now, what about negative numbers? The numbers from 0 to -3 also work because their absolute values are less than 3. For example, -1 has an absolute value of 1, which is less than 3. That means it fits correctly. All the x values that satisfy our inequality can be found here in the interval between -3 and +3. Notice that we can't go any higher than +3 or any lower than -3 because any of these numbers will have absolute values that are greater than 3.
We can write the solution for our inequality in interval form, just like the others we've done. Parentheses -3, comma, +3, parentheses. Or we can write it like this. X is greater than -3 and less than +3. Both of these mean all numbers between -3 and +3, which are the numbers that satisfy our inequality. See how that all ties together?
Okay, say we've got the absolute value of x is less than or equal to +4. We know the lowest value we can possibly have for x would be -4, because anything beyond that has an absolute value greater than 4, and this would make our statement incorrect. See how the lowest we go is just the negative version of the number in our inequality. The highest we go is positive 4. So, our interval is bracket -4, comma, positive 4, bracket. And our breakdown looks like this. X is greater than or equal to -4 and less than or equal to positive 4. On the number line, we've got filled in circles at -4 and positive 4, and we shade the line between them. All of these numbers satisfy our inequality.
Okay, now we're going to do one that's a little bit different. Our first two examples involved less than or equal to. But what if we had the absolute value of x is greater than 3?
Well, this tells us that the absolute value of whatever number x stands for has to be greater than 3. So any positive number greater than 3 will satisfy our inequality because its absolute value is greater than 3. But remember, we've got to figure out which negative numbers will have absolute values that are greater than positive 3 as well.
Well, all numbers less than -3 will work because their absolute values will be greater than positive 3. For example, if we pick -7, the absolute value of -7 is positive 7, which is greater than 3. Same thing with -138. The absolute value of -138 is positive 138, which is greater than 3.
So we've got two parts to our number line this time. We figured out that x can be greater than 3 and also less than -3. This means we've actually drawn the interval from -3 to -infinity, and the interval from positive 3 to positive infinity, or x is less than -3, and x is greater than positive 3. These are the numbers that will satisfy our inequality.
I know it seems long, but once you do a few of these absolute value inequalities, you'll be breezing through them, and you'll want to do them for all your friends at birthday parties. So let's do one more to get the hang of it.
Say we've got the absolute value of x is greater than or equal to 1/2. We handle this one just like the last one we did. We know that we're going to have a two-part answer because of the greater than or equal to symbol. We know all the numbers from positive 1/2 to infinity will work because their absolute values will be greater than or equal to positive 1/2. But all the numbers from -1/2 to -infinity will also work because their absolute values will also be greater than or equal to positive 1/2. So we've got the interval from -1/2 to -infinity, or x is less than or equal to -1/2, and the interval from positive 1/2 to positive infinity, or x is greater than or equal to positive 1/2. These are the numbers that satisfy our inequality.
All right. We've reached the end of the number line circuit. Let's take a quick look back.
In Part 5, we've looked at putting inequalities and absolute values on a number line. With greater than or less than, we use an open circle at our number. But if we're talking about greater than or equal to, or less than or equal to, then we fill in our circle. Parentheses mean greater than or less than, and brackets mean greater than or equal to, or less than or equal to.
The sign for infinity looks like a number 8 napping. It can be positive or negative. Positive infinity deals with the right side of the number line, while negative infinity deals with the left. And if we see this, it means the set of all real numbers.
Remember, when we put absolute values on a number line, we've got to consider both the positive and negative versions. So, we'll always have two values, a positive value and a negative value.
Well, that's all we've got room for in Part 1. Remember, we've covered integer exponents, prime factorization, tree diagrams, absolute values, square roots, fractional exponents, and inequalities. Since you've gotten this far, you must be ready for the sequel, Pre-Algebra Part 2, where we start to scratch the surface of big, bad old algebra with things like linear equations, graphing, absolute value equations, and linear inequalities.
We hope the pumped-up world of pre-algebra helps you get where you need to go.
If you have any questions, make sure you give us a call here at 1-800-238-9669. We'd love to hear from you.
Hey, you know what? We had a great time, but now it's time to get on with the grind.
There's more tapes to be made.
Yeah!
And be sure to check the store for other Standard Deviants titles like
The Really Big World of Astronomy, The Adventurous World of College Algebra, The Deep Fried World
of Organic
Chemistry,
and the Anatomically Correct World of
Anatomy.
There's so much more than that. Much more.
Bye-bye.
Thanks for watching.
you.